Okay, guys, here we are at section 10.3, geometric sequences and series. So we just went over what an arithmetic sequence was. That's when you add or subtract to go from one term to the next. Well, geometric sequence is a sequence in which each term after the first is obtained by multiplying the preceding term by a fixed non-zero constant. So it can't be zero. All right, but if I multiply it by anything, it will be a geometric sequence. So the amount by which we multiply each time is called the common ratio. Now the common ratio is going to be represented by a lowercase r of the sequence. So here are four examples of a geometric sequence, and I want to see if you can see what the common ratio is. Well, what are you multiplying if I start with 1 to get to 5 to 25 to then multiply this by that same number to get 125 and 625? So if you remember to find a common difference, we could take the second term and subtract the first. Well, the same thing's kind of similar here. If I start at A1 and I multiply it by some common ratio, that's going to give me A2. So to find R, and then I'm going to take A2, multiply it by that same R to get A3. And then take A3, multiply it by the same R to get A4, the fourth term. Well, to find R, we could divide each side by A1, and R is going to be the second term divided by the first term. Or it's got to be the same value. If it's the same value, R has to be the third term divided by the second. And also take the fourth term and divide it by the third. Now, if all of these give you the same ratio, then it's pretty much the same number, the same constant R, then it should be exactly that, a geometric sequence. But always check to make sure that the pattern is consistent all the way through the sequence that is given. So if I wanted to find R here, now you probably could tell that R is 5, but you take the second term, which is 5, and divide it by the first, and that's 5. You take the third term, divide it by this previous term. 25 divided by 5 is 5. And I take the fourth term and divide it by the third term. Now, really, I'm going to be honest. So if I divide that by 25, $1.25 divided by 25 cents is 5 quarters. All right. So a lot of times what I'll do is if I think it's 5, by going 5 divided by 1 is 5, I go 5 times 5 is 25, multiply that by 5 is 125, and so on. And if it's consistent through, then that's the common ratio. But you can always check algebraically. So the common ratio here is 5. What is the common ratio here? Am I adding? So a lot of times we don't know if it's arithmetic or geometric. So if I add 4, I get 8. If I add 4 again, that gives me 12, not 16. So right now I know this is not arithmetic. 4 times what is 8? 2. Well, what's 8 times 2? 16. 16 times 2, 32. So right now I kind of figured out that R is 2. All right, it's not arithmetic, this is geometric. But if I wanted to, second term divided by first, you get 2. Third term, 16 divided by second term, 8, which is also 2. And then you might as well do 32 divided by 16 to show that that is also 2, meaning R here, the common ratio is 2. Now here, you might see, what are you multiplying to get to the next? That's the pattern you're looking for. And a lot of you are going to see this without doing this work, but sometimes it gets complicated. So I can go second term divided by first, negative 12 divided by 6 is negative 2. And then what I'll do is I'll go negative 2 times negative 12, positive 24. 24 times negative 2, negative 48. So we can do it that way, or we can go 24 divided by negative 12. Well, that's negative 2. Negative 48 over 24, well, that's negative 2. And then negative 2 times negative 48 is positive 96. Now, this is where you're like, well, I know what I'm dividing by, but what's the common ratio? Well, the common ratio is what we multiply to each term. So if you could see that you divide by negative 3, well, you know what? You can say the common ratio is just a reciprocal, which is negative 1/3. All right, because that's multiple. A division is just multiplying reciprocals. But if I had a little trouble, second term divided by the first, and that does reduce to negative 1/3. If I went third term divided by the second, well, that's already negative 1/3. All right. And the third term, r equals negative 1/3 divided by 1. Well, that's negative 1/3. And if I wanted to do 1/9 divided by negative 1/3, well, that's 1/9 times negative 3 over 1. You multiply the reciprocal, which is negative 3/9 or negative 1/3. So in this case, r is negative 1/3. In this case, r was negative 2. So you should be able to find a common ratio by just performing these operations right here to give you an idea about how to, start up your problems that you're going to be getting. So in example 1, we get into something that deals with the recursive formula. Now it's not written that way, but write the first 6 terms of the geometric sequence with the first term 12 and the common ratio of 1/2. So if I were to write a recursive formula to find any term, what we're really going to do is you take the common ratio and you multiply it to the previous term. And that's really what we're going to do. So this is actually not written in a form because they do give me the first term. A1 is 12. And I got to find A2, A3, A4, A5, and A6. What do these all equal? Well, if the next term has a common ratio of 1/2, we're going to find A2. You take the previous term, 12, and you take the common ratio of 1/2 and you multiply it to the previous term, which is 12. And half of 12 is 6. So I know this is 6. Then find A3. We take the common ratio of half and multiply it to the previous term, which is A2. And that's 6, which will give me 3. Then A4, you take 1/2 and you multiply it to the previous term, which is 3. And that's just, put this over 1, 3/2. Okay. Now it's starting to get serious. Not a big deal, guys. A5. And this is why you'd rather have fractions than decimals. This makes it so much easier. 1/2 times the previous term, which is 3/2. And that's just going to be 3/4. Okay, that wasn't so bad. 1 times 3 is 3. 2 times 2 is 4. And A6, you take the previous term, you take 1/2, multiply it to the previous term, which is 3/4. 1 times 3 is still 3. 2 times 4 is 8. And you get 3/8. So my last statement, or my final answer, is 12, 6, 3, 3/2, 3/4, and 3/8. Now, what you're going to find with geometric sequences, if the common ratio is positive, but not 1, because 1's not going to do anything if you multiply something by 1, you're going to see either exponential growth or exponential decay with your terms. Now, this would be exponential decay. You start at 12, then 6, then 3, then 3/2, which is 1.5, then 3/4. And you can see that this is actually approaching, if you keep taking it, it's actually going to approach a horizontal asymptote of y equals 0, the x-axis, because it's just going to get closer and closer to 0, but never ever touch it unless you go out infinitely. All right? And we're going to get into this a little later on about your common ratio being between 0 and 1 when we talk about series and stuff. But for now, I want you guys to try checkpoint 1. So we get into a general term of the geometric sequence formula right here. Now, this is just a way we can write an explicit formula. So if I had to find the 15th term, we just substitute in 15 instead of being recursive. But a lot of these geometric sequences, they really don't, they either grow very, very fast or actually, like the last question, they drop and approach 0. So we generally only stick around maybe 10th term. We're not really going to find a 300th term because that would be very, very large or very, very small. So a lot of these, you could take this example here, find the 8th term of the geometric sequence whose first term is -4 and a common ratio of -2. I mean, really, if you multiply -4 times -2, that would give you the second term. Multiply by -2, that would give you the third term, and so on. It does become redundant, and you're going to find yourself just miscounting, counting to 7 instead of 8, or not counting the first term as 1. You're going to multiply this 8 times, which will give you the 9th term. All right, but that's where we come up with this general term formula right here. All right, so a sub n again is the term you're looking for, so it's the value of the term you are looking for, or it's the last term. And we're going to be, it depends on how we use this formula. A1 is still the first term. And R, we just talked about, is the common ratio, what you're multiplying, common ratio. All right. And N is the number of the term. Okay. So if I want to find the eighth term, that's going to be N. So what I'm going to do is I'm going to rewrite this to find the explicit formula and then figure out what the eighth term is. So when we write the explicit formula, we're going to need values for A1 and R. So when I look at this, it says the first term is -4. So that means your first term, A1, is -4. All right. And R is a negative number too. So R is -2. So you're multiplying by -2 to get to that term. So when I set this up, it's A sub n equals -4 times R is -2 n to the n minus 1. Now, I did make one big mistake here. Anytime your base, and I would do this for every time, your base to your exponent is a negative value, okay? You want to plug this in, all right? Now, this is not an exponential because your base in an exponential can never be negative. So this is only going to be an exponential if your base is a positive, if your R is positive. Otherwise, it's going to, every time you multiply by a negative, it's going to skip above and below the x-axis, going positive, negative. Then the next term is positive. The following term is negative. But this is our explicit formula. Now, they want me to find the value of the eighth term. So what is A sub 8? Well, it's -4 times -2. Now, you're going to plug in 8 minus 1 there. Now, 8 minus 1 is going to be 7. So it's -2 to the 7th power. Now, it's 2, 4, 8, I almost said 6, 16, 32, 64, and 128. So I'm going to have to do some crazy math here. Not crazy, but math I don't feel like thinking about right now. So at this time, I am going to put on my calculator. And when I type this in, it's going to be in parentheses, -2, close it to the 7th. And that's going to give me -128. So you got -4 times -128, which would be times -4, and I get 512. And this will be my eighth term. Now, is it easier to go -4, then you're going to get 8 when you multiply by -2, -16, 32, -64. So you're going to go times -2. So let's see. It's -64 times -2, and I get positive 128. But if you label this A1, A2, A3, A4, A5, A6, then I multiply this by -2, I get -256, and multiply that by, that's my 7th term. My 8th term is going to be, multiply this by -2, the previous term, 512. Now, I think that this way is easier with many of the problems we're going to do, so please don't do this. I mean, if you're taking a test and you need to come up with the answer and you do this, that's fine. But for the arithmetic, it's going to be, what's the 300 term? This becomes redundant, and it takes a long time to kind of write out all 300 terms, and I've seen kids do it, but they spend all that time +2, +2, +2, and then counting. But I've also seen kids miscount, or they make this term number 9 or 7 because they forget to count this. So they go, I multiply by -2 once and I get -8. Multiply by -2 again and I get -16. Multiply that by -2, I get positive 32. And they're only on the third term where that's your fourth term because they forgot A1 was -4. So what I want you to do is use the formula, and this was example 2. Try checkpoint, example 2. Try checkpoint 2. Okay, guys, I'm in my garage, so you hear the furnace in the background. All right, sorry. So in example 3, this table shows the population in the United States in 2000 with estimates given by the Census Bureau for 2001 through 2006. So every 10 years, the U.S. does the Census Bureau and sends it around to all the houses and stuff. Who lives there? What's the income? Your parents probably got it in the year 2020. It was all out last year. You fill it out, you send it in, and every 10 years they gain an idea of the population and the socioeconomic status of that surrounding area, with how much people make, who's living there, how many people, and they generally get an idea of what's going on in the economy. So, first question is, so in 2000, 2001, 2002, what I notice here, it says this: the population is in 2000 was 281.4, but it's a rounded estimate. Obviously, they're not going to get the exact amount because not everyone's honest. You know, you might have five people live in your house and one person you don't want to get caught because he's paying rent. I don't know, but you don't tell. It's not an accurate thing, but it's an estimate. They really do get a really good idea of how many people live in that surrounding area. So this point 281.4, this is in millions. So in 2000, it's actually 281, million. So it's point 0.4, so that's going to be 400,000. And obviously, it's not going to be this perfect, but that's an estimation there. So when you think of millions, that's 281 million, and the point 0.4 is just what it would be in the 100,000 spot. All right. So they want me to show that this population is increasing geometrically. Well, you guys probably did this in your head on the last one. What do you multiply this by to get to this term? And what do you multiply this by to get to this term? Ah, so if you remember, we can always find a common ratio by going your second term minus divided by your first term. So if I did what is 284.5 divided by 281.4, let's see what we get. 284.5 divided by 281.4, if I can only type in correctly, I got 1.011. 284.5 divided by 281.4. All right. So this right here, what this means is actually your population has grown by 1.1% because it's 1 plus the rate. And if this is your rate, and now this keeps going, it's not a nice number. That value keeps going. But I want to show that it gets this number. Let's do this 0.16347. And it's not going to be an accurate thing. So let's see. Does that occur for R equals A3 divided by A2? So let's see. What is 287.6 divided by 284.5? So 287.6 divided by 284.5, and I got something a little different, 1.0108969 09. Now they're not accurate, but again, these are rounded estimates that they're using to kind of generate like where's it going to be in the future. And let's just do the next one, A4 over A3. Your fourth term divided by the third. So that's 290.8 over 287.6. So 290.8 divided by 287.6, and I got 1.011126565. So obviously they're not going to be exactly the same. But if we went to the 100 spot, and we'll just do this, we'll count R as really 1.01. That will really help us figure out the rest. And it's going to be more than one because it's growth. And when it's growth, the rate has to be bigger than 1. Decay is anything between 0 and 1. So I know now that this is really a geometric pattern. Even though these are not exactly the same, you're not going to get that because these are, where does it say? Estimates that were given. All right. But they all would round to this value right here, which is pretty close, saying it grows by like 1% every year. All right. So write a general term geometric sequence, O and B. So that's the form of A sub n equals A1 R to the n minus 1. And then we'll do part C in a second. So write a general term for a geometric sequence modeling the population of the United States in millions n years after 1999. Now, I kind of wrote this out. While I was writing it out, I realized that this was going to be A1 because this is 1 year after 1999. This is A2 because 2001 is 2 years after 1999. So I'm replacing this N with that subletter. This would be A3, A4, A5, A6, A7, and then we'll predict what it would be in 2009. So to write a general term formula, we just need these two variables, A1, which is going to be, and I made this A1. This is A1. The value, I wrote it wrong way. So that's A1. This is A2. This is A3, A4, A5, A6, and A7. All right. This would actually be, so that's A1, N equals 1. This is N equals 2, N equals 3, N equals 4, N equals 5, N is 6, N is 7. So the seventh year would be 2006, 7 years after 1999. So to write my general term form here, it's going to be A sub n is the value of A1, 281.4, and it said to leave it in millions. So I'm going to leave it as this decimal. So that's 281 million, 281.4 million, times my common ratio of 1.01 to the n minus 1. So this is my general formula right there. So like any equations we ever wrote, this is going to be this is bigger than 1, so this is actually exponential growth over the years. So I have think about this as being y, and that's x minus 1. Just like you would have that in a regular equation. So in C, it says, well, what's the projected U.S. population in millions for the year 2009? All right, well, 2009. So let's see. What is the value of n in 2009? So n is that many years after 1999. So if I went 2009 minus 1999, I would get 10. All right. So n is 10 here. So if I want to find the 10th term, I would use this general form here, 281.4 times 1.01 to the 10 minus 1. Now, I know 10 minus 1 I could do real quick. That's going to be 1.01 to the 9th power. All right. So let's see, 281 let me just do 101.01 to the 9th power. And I'm going to get some crazy number, 281.4 times 1.093685273. And when I multiply that by 281.4, I get 307.7630357. Now, I would tell you what to round to. They don't hear, so I would say 307.8 million. Now, again, you just saw me round, just like they rounded these values. So it's really hard to get an exact common ratio with rounded values, but you could approximate just to generate an idea, even with these estimations. And we can see what it's going to be. Now, if I went 300.5 times my common ratio, 1.01, I get what it would be for A8. Now, I want to do A9, so I multiply that by 1.01, and that gives me what it would be in the year 2008, which would be A9. And if I did it one more time, you could see that I am kind of off here. All right, I am at actually 309. So you can see that this is not always going to be exactly that. But if you use this equation here in this general form, you can get a very accurate answer, and we can use it to predict what happens later on. Give checkpoint 3 a shot. Okay, so here we go. What if we wanted to find the series of a sequence of geometrics? Well, series is a sum of that sequence. So if we want to find if it was a geometric sequence and we want to find the sum of those terms, we can use this formula here, where S of n is the sum of the n terms. A1 is still the first term, R is the common ratio. And again, n is the number of the terms. So if I'm looking for the sum of the first 18 terms, n's going to be 18 because there's 18 terms. Now, I wrote it this way because I've seen on the Algebra 2 Regents, they do give this as part of the reference sheet. So they just distribute the A1 through. It's really not much of a big deal, but maybe you saw this as opposed to this. They both mean the same thing. But what I want to point out here is you don't need to find, like we did in the arithmetic, that last term, that 18th term. All right? All we need is this information here. So if I want to find the sum of the first 18 terms, well, I need to find A1. Well, A1 in this case is 2. That's my first term. I need to find R. Well, what am I multiplying to get to the next term? Now, again, I can go, you could probably see this one after the last one. Negative 8 divided by 2 is negative 4. 32 divided by my second term of negative 8 is negative 4. And if I did negative 128 divided by positive 32, that is also negative 4. So I know R is going to be negative 4. All right? And I know that n is 18. I'm looking for the 18th term. So it's your first term times 1 minus your negative 4. You put R in parentheses when you do this, and you get 18. All right? Over, in parentheses, over 1 minus R, negative 4. Now, what you got to be careful of here is that this does have alternating signs. So whatever I add here, I'm going to subtract a bigger number here, then add a bigger number. So even the sums are going to be even odd. Now, since the second number and the fourth number are negative, that last number 18, I'm looking at the even terms. Second, fourth, sixth. 18th term is also an even number. That's going to be a negative number. So if your last number is going to be the absolute value, that's going to be so huge, whatever that value is, negative or positive, it's going to have that value at the end. So this should have a negative sum at the end. So when I do this, the first thing that shocks me is, what is negative 4 to the 18th power? That's going to be a huge number. 1 minus, well, negative 4 to the 18th. First off, I know it's going to be positive, but I'm subtracting that positive number to the 18th. And I get this number that says 6.8719476674 e to the 10th. So remember, this e to the 10th on your calculator just means scientific notation. So it's 6.8719476674 times 10 to the 10th power, which means if I move this over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I'll put a 0 there for now, but this is actually what this number would be here. I'm putting a 0 there, but it's rounded somewhere there. And that would be this number here, all right? We're talking about 68 billion something. So if the number is that big, you're just going to put that value in for now. So I'm going to put 6.871947674, and then put like times, or you could put e, you could leave it as e to the 10th. We're not going to go this large, guys. All right? Over 1, this turns into a plus 4, which will give me 5. Now, I am going to do myself a favor and store this number as x. Whoop, I didn't do myself a favor. Enter store as x. So now I want to go and take your time with this math, even though you're rewriting this. This is going to save you a headache later on. What's 1 minus that number? So I got 1 minus x in my case. And I get negative 6.871947674. Actually, now it says 64767 e to the 10th. All right. So I lost a digit here because the negative took up one of the slots there. So, and this is still divided by 5. I really don't know what this number is going to give me, but I'm going to go 2 times that number. So 2 times my answer. And I'm going to get negative 1.374388953 times 10 to the 11th power. over 5. And I'm hoping that when I go divide it by 5, it's going to make this a little easier to read. Negative 2.748777907 e to the 10th. So at this point, I am definitely going to approximate, and I'm going to write this as negative 2. So I move this over 10. 1, 2, 3, 4, 5, 6, 7, 8. And I'm just going to tack on 2 zeros to approximate. So it's 274,877,907.00. And this is an approximation. The checkpoint is going to be a lot easier for you to do, but just note the idea. Don't get too hung up on this huge number. It doesn't get that huge in this course. So just kind of know that we're just going to leave this, use that value, and we will get some crazy number here. But that just shows you how exponential this grows, if how fast this grows when it's geometric. Try checkpoint 4. So if I take a look at example 5, it wants me to use the summation notation to find 6 times 2 to the I from terms 1 to terms 10. So remember, how many terms is that? If it's from term 1 to term 10, because you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you take the difference and you add 1. So for the number of terms, it's the difference between your top term, your lower term, and then add 1. So that's just 9 plus 1, which is 10. Now that's kind of like a no-brainer for many of you, but that's sometimes when this starts at 3 and that's at 55, you go 55 minus 3 is 52, but there's 53 terms. All right, so that's why you want to get used to knowing how to find n by taking the difference and adding 1. It's just obvious, which kind of is the point. So if I had to do this, I noticed that this is in a geometric nth apparent formula, or the explicit formula, where you got your first term times the second, an r to the exponent. It's in that type of form where it's an exponential. Now, this is not your first term in this case, because this is not I minus 1. This is just I. So it's not your first term, all right? You'd have to plug 1 in to find your first term. So if I were to do this, this is 6 times 2 to the first, plus 6 times 2 to the second, plus 6 times 2 to the third. And really, all you're doing is you're multiplying this by 2, because this is 6 times 2 times 2. And then you're multiplying this 2 squared by 2 to get here. So R is actually a common ratio. And I would keep going until I got to 6 times 2 to the 10th power. So R is your common ratio. So what am I multiplying to go from here to here? Well, maybe you need to do the first few terms to see that it's 2. So if I did this, this is 6 times 2 to the first, which is 6 times 2, which is 12. 6 times 2 squared is 6 times 24 times 4, which is 24. 2 cubed is 8. 6 times 8 is 48. And you can see, you are multiplying by 2 to get to the next term. And then you're really going to go 6 plus ... plus 6 times 2 to the 10th is 1024. So let's see, 2 to the 10th is 1024. And then multiply that by 6, and it's going to be plus 6144. And we could do it this way. But I noticed that this is a series of a geometric sequence. So if I take a look, the formula is to find it, I could take the first term, then it's times 1 minus r to the n over 1 minus r. So I realized that my common ratio is your second term divided by the first, 2. And your third term divided by the second, it's 2. And I could do the fourth term, but I'm not going to. I can see I'm multiplying by 2 just by seeing that. You multiply this by 2, you get 2 cubed. Multiply 2 cubed, you get 2 to the fourth. That's going to be the next term. So R is 2, N is 10, and I had to plug in 1 to find out what A1 was. And A1 is 12, and you had to do the first one there. I didn't have to do the last one because the sum formula for geometric sequence doesn't include the last term. So if I want to find the sum of 10 terms, because that would be 10, it's equal to your first term 12 times 1 minus 2 to the 10th power, because my number of terms is n, over 1 minus r is 2. So it's going to feel weird that you're adding all these positive numbers and you're going to divide by a negative. What's going to end up happening is this numerator is also going to be negative. All right? So, Mike, and this is kind of strange. If you keep adding positive numbers, you're going to have a positive sum. But this will turn into a positive sum because this is 12 times 1 minus 2 to the 10th is 1024. So that's 12 times, that's going to be negative 1023 over negative 1. So let's see here. All right, so times that by 12, the negative 1023, and I get negative 12,276. So negative 12,276 divided by negative 1 gives me a sum of 12,276 for my final answer. All right, and we could use the fact on our calculator, the summation button, math, go to summation, and that's going to be, again, I'm going to pick x for my variable, equals 1, and then it's going to be, I'm going to 10, so I type 10 up in my numerator, and then for my expression, I'm going to put 6 times 2 to the x power, because I chose on my calculator 2 to the x. And hopefully I didn't make a mistake, because when I enter, I get the same answer that I got, well, not above my calculator, because I didn't divide this by negative 1, but on the board here. I would get that answer there. So give example 6 a shot, not by the calculator method. That's a check, using this method here. Okay, guys. A union contract specifies that each worker will receive a 5% pay increase each year for the next 30 years. That's pretty big. All right. One worker is paid $20,000 the first year. What is the person's total lifetime salary over a 30-year period? So that means, what did they make year 1, year 2, year 3, and put it all together. What did they make all together? So this is going to be a sum. Now, anytime anything goes up by a percentage or down by a percentage, you're dealing with a geometric pattern, all right, an exponential pattern there. So I know that in 2000, okay, and try to guess what the rate is. I already know what it is, and you should too, but I'll go over it. So this would be the first year. That's A1. What would A2 be? Well, if it's a 5%, you're going 20,000. What's 5% of 20,000? So that's 0.05. We turn that to a percent. Of means multiply. And then you're going to go 0.05 times 20,000. And that's $1,000. So that's not what they make the second year. That's what it's increased by. So then you're going to go 20,000 plus the 5%. And year 2 is going to be $21,000. All right. And year 3, you're going to get a 5% of your 21,000. So what's 0.05 times 21,000? So if I went 21,000 times 0.05, or 0.05 times 20,000, I get $1,050. So now you get your 21,000, and you went up $1,050. All right, so now you're going to get $22,050. So year 3, or A3, would be $22,050. So the question here is, if I got to find the sum of this geometric pattern, that's the sum of this many terms is A1 times 1 minus r to the n over 1 minus r. So I already know n is 30 because I'm looking for a 30-year period. I know my first number, my first term, or the first year salary was 20,000. The one thing I don't know is, what is r? Now, I know what r is just from doing percentages all the time, but what is r? So we can always find r by going second term divided by the first, 20,000. So if I did 21,000 divided by 20,000, whoop, come on, I missed a zero there. you get R is 1.05. Now that's kind of weird here because it was 5%. Where did the 1 come from? All right. Now if I did 22,050 divided by 21,000, these should be equal. Third term divided by the first. So 22,050 divided by 21,000, I get 1.05. So R is going to be 1.05. All right. Now, why is that? Well, let's take a look here. We'll just deal with this one right here. What we're going to do is we're going to work backwards. How did I get that 21,000? Well, you went 2,000 or 20,000 plus 1,000. And I'm going to erase this in a second. Now, how did I get that 1,000? Well, I have this 20,000 here. Plus, I did 2,000 or 20,000 times 0.05. Now, if you notice here, you actually have a greatest common factor of 20,000. So if we take that out, what you're left with is 1 plus 0.05. So to get to 21,000, you multiply the 20,000 by 1 plus the rate, which is 1.05. All right, so I knew that it was an increase by 5%, so you just multiply by 1 plus the rate. All right, and you've seen that in the formula where A is equal to P times 1 plus R to the T. 1 plus the rate for exponential growth. The K was 1 minus the rate. So I could see that this is going to be growth. So I'm going to erase this here. I found R, and now let's find out what this person is going to make over 30 years. So it's 1 minus 1.05 to the 30th power over 1 minus 1.05. So I'm going to get some crazy number with this decimal, but I'm just going to write it out. I'm going to have to backspace this S of 30 here because I'm going to have a big decimal, I believe. And it's going to be 1 minus 1.05 to the 30th. Now, you really want to store things in your calculator here. So you get 4.321942375 over 1 minus 1.05 is negative 0.05. So that's going to be 20,000 times, what's 1 minus this number? So I'm going to go 1 minus second negative for the answer above, and it's going to be an exact negative 3.321942375 over negative 0.05. So now I'm going to go 20,000 times this. So times 20, 1, 2, 3 for the 1,000. And I get negative 66438.8475 over negative 0.05. And now I'm going to do my division of divided by negative 0.05. And I get 1328776.95. So this is approximately 1328776. I'll make this to the nearest $7. So over 30 years, this person's making almost $1 million cumulative over that 30-year period. All right. So I would like for you guys to try checkpoint 6. Okay, guys. Now, this is the fun part of math. All right. So we got this crazy formula here. And what this represents is the value of an annuity, interest compounded n times per year. So really think of this. This is like an IRA account. So let's look at this example. Before we look at example, the formula. Well, A is the final value of the account. What this account's going to be worth at the end. P, in this case, P is going to be the deposits made periodically. So in this case, they're putting in $200 a month. So it's the payments paid periodically. All right. So it's going to be the same amount as the compoundings periodically for a specific period. We're doing it every month. R is the rate as a decimal. So you got to know how to convert a percent to a decimal. N is the number of compoundings a year. Like, how often is this rate being applied? And in this case, it's compounded monthly. So if it's compounded monthly, how many times a year is that? And that would be 12. And T is the number of years you're going to invest for. Now, this is not like the other formulas we learned in the exponential section earlier in the year, because that was like if you inherited like a lump sum and put it in, what would it be 30 years from now? This is something that I do and most people do when they start to retire. They take a chunk of change from their paycheck, and if you work at Target, $200 a month is going to be a lot. But when you start making, and way more than me, you're starting to make, say $5,000 a month. Some of you are going to be making that. You can take $200 out and invest it into this IRA, which is generally a safe investment. Now, stock markets go up and down, and you're going to see your payments go up and down. But we're really looking at a 7.5% is generally a fixed, the best fit exponential over a 40-year period or 30-year period or 20-year period. So that's really just an idea of how often that's effective. So at age 25, to save for retirement, you decide to deposit $200 at the end of each month into an IRA that pays 7.5% compounded monthly. So I want to know how much from this IRA, how much will you have from this IRA when you retire at 65? So I'm looking for A, what is the final value? What are the payments we're making per month? And you can see you're putting $200 in a month. So that's your P. The rate is 7.5%. So when you move the decimal over twice, R is going to be 0.075. All right. Don't put 0.75. That's 75%. That would be a really good investment. Not going to happen. All right. N is the number of compoundings a year, and you can see it's compounded monthly. So that would be 12 times a year. That means they apply the interest rate at the end of every month when you make your payments. You put it in, they apply the rate, and you're building off the interest that you made. So if you put in 200, the next time you put in, you're going to put 200 in more. But if you make 7.5%, you're going to add on the 7.5. So after 2 months, it's going to be $400.50. Then you put what's 7.5% of this, add that to it. This is not the money you're going to make. It's the interest that keeps accumulating, and you're putting this percentage on the interest that you're making. So that's really what you want to know is at the end, what is the interest? What did you make besides your payments? So first, let's figure out what the value of this account is going to be. And how many years are we doing this for? Well, in this case, they're starting at 25 and they want to know at age 65. So 65 minus 25 is 40 years. So for 40 years, they're going to make this investment. And trust me, once you get this out of your paycheck, you don't even realize it's gone. Like it's just automatically put into an account, right? Withdrawal. You don't go to the bank and put it in every month for 40 years. You get it taken out, you don't see it, and you'll be fine. So if I want to find this, what is the value of the account if I put in $200 a month? So that's 1 plus the rate is 0.075 as a decimal over 12 to the, and this is in parentheses, 12 times 40 minus 1 over 0.075 over 12. So this is going to take a little bit of time, but I'm going to start with the parentheses inside. So 1 plus 0.075 divided by 12. And I get 1.00625. Now 12 times 4 is 48, so just tack on a 0 to the 480th power minus 1 over, and if I did this real quick, I'll store this value, 0.075 divided by 12, you're just going to get 0.00625 because you didn't add the 1 there. So it's 0.00625. So that's going to be 200. And now I'm going to go 1.0625 to the 480th power, and I get 19.898888859 minus 1 divided by 0.00625. So this is 200, and now when I subtract 1 from this, it's just going to be 18.898888859 over 0.00625. So what's 200 times that? And I'm going to get A equals 3779.777718 divided by 0.00625 divided by 0.00625. And this account is going to be 604764.4348. All right. So what is this about right there? Well, it's really about 604,760. I'll leave it as 4. Okay. So if I did that right there, what do you think? So that would be what's the value of the account after 40 years. Now you're going to find yourself putting more money than the 7.5%. You can maybe get a better interest rate. You can put more than 200 in when you get. So once you start with 200, after 10 years, you're going to get pay increases. Bring it up to whatever you can bring it up to. Bring it up to 300 or whatever is not going to break the bank. But the question here is, what's the interest? So this is the value. How much money did you make? So think about just putting money into your bank account now. You get your bank statements and you make 2 cents for like 3 months. Like, what is that? And then the next one, you make maybe 2 cents. It's not really such a great to leave your money in KeyBank. That's great for convenience, writing checks, get money out fast. This is really where you want to make your lifetime retirement investment. All right. So how much did this person make? Well, let's think about it. What did they spend? Well, they spend $200 every month. So if I went 200 times 12, that means every year they did $2,400. All right. But they did that for not just 1 year, they did it for 40 years. So if I did $2,400 times 40, that means they spent a total of $96,000. They just kept putting aside, not touching. So the interest is $604,764 minus the $96,000 that they put in, because they didn't really make this money because they invested that much money. So how much money did this person make in this account by doing absolutely nothing? So you end up getting $500,000, $500,000 by just letting the bank do the work for you in this IRA. And obviously you can put in more money, you can get better rates, and there's ways that you can always invest and increase your investments as you go. But the earlier you start, the better you're off. So making this much money was quite a thing. All right. In this case, give Checkpoint 7 a shot. Okay, guys. So the last thing we're going to talk about in this section is the sum of an infinite geometric series. So this is really saying if this series kept going on and it was infinite, we could actually find the sum if and only if the common ratio is in this domain right here. So that means anything that's bigger than 1 or less than -1 will not work. So it's got to be a fraction where it's less than 1. So really, you got the absolute value of r is less than 1. All right. So if it's -1/2, we can find it. If it's 1/2, we can find it. But if it's 1.5, no. -1.5, no. The only way we can find the sum of an infinite series for a geometric infinite series is if the common ratio is in this domain. If the absolute value of r is greater than 1, then the infinite series does not have a sum. So if you were just going, what's 2 plus 4 plus 8 plus 16, that's just going to keep getting larger and larger, and grow up to infinity. But when you have a ratio that's between, if you kept adding the sums, it actually approaches an asymptote. And that asymptote would actually be the sum. Okay? If you went out forever, they'll say eventually you would, which you can't really do, but if you went out an infinite amount of times, the theory of limits is going to say, wow, you would actually have an actual sum. So they want me in example 8 to find the sum of this infinite geometric series. So they wouldn't ask me. First they tell me it's a geometric series. So I don't, to find r, what do you multiply this by to get this? Well, we can go second term, which is negative 3/16. Because what are you adding? A negative 3/16. And you're dividing it by 3/8. So that's going to be negative 3/16 divided by 3/8, which is negative 3/16 times the reciprocal. So this ends up becoming, reduce this to negative 1, that's 1. That 8/16 reduced 1/2, r is negative 1/2. And if I multiply negative 3/16 by negative 1/2, I get positive 3 over 32. So I can see that this is it. But now that I have this, I can use this formula. Your first term is 3/8. Now, for the other sum, there was an n here. Here there isn't because there is no number of terms. It's just the sum of an infinite amount of numbers. And that's going to be found by going your first term, 3/8, over 1 minus r. And r in this case is a negative 1/2. So this is going to be 3/8 divided by 1 plus 1/2. So 1 plus 1/2, if you make this 2 over 2, is going to end up being 3/8 over 3/2. All right, so that's 3/8. So S equals 3/8 divided by 3/2. When we divide fractions, you multiply the reciprocals. And these cancel, and you end up with 2/8, which is, sum is going to be 1/4. So if you kept adding this pattern here of numbers with a common ratio of negative 1/2, you would eventually get to the sum of 1/4. All right, give checkpoint 8 a shot. All right, guys, we are good. I will see you next time. Take care.